Hi everybody, and welcome back to Digital Integrated Circuits. I'm Dr. Adam Teman of the EnICS Labs at Bar-Ilan University. This is Lecture 4, Design Metrics. So, my lecture outline today has only 3 short parts: design abstraction, a reminder about basic design metrics, and then a focus on the cost of integrated circuit. So let's start with design abstraction. So basically in every engineering process we have design abstraction levels that help us make a complex network or a complex product where each design team or designer has to focus on their own part. They have to kind of black box it and have some sort of interface to the abstraction levels that are below them and above them, but they need to focus on what they are experts at. In our field, we can often divide it in the following way. So first of all, we have the device level abstraction, where we actually deal with the devices themselves, the transistors, resistors, whatever process technology. Then we can take the devices and we can build some circuits. For instance, here we have a CMOS inverter that's built out of a number of transistors. Once we build our circuit, we can abstract it to a logic gate or some sort of basic other type of a structure that we know how it works without going into the actual details of what the innards of the actual transistors that are connected are. On top of that, we can take the gates and build some modules, and here we show an adder that is built of several of these digital gates. And finally, we can go up to the system level that uses many of these modules to build a whole system. Let's go into detail about these different types of abstraction levels. So starting with the device level. Basically, as we have mentioned quite often in the course, we have these fabrication plants, fabs or foundries, and they supply the process design kit. The foundries, they do the whole technology. They make the devices, they characterize them, they know how they work, they know what they offer. Their interface to the next level, which is the circuit designers, is this process design kit. The process design kit includes devices such as transistors, resistors, capacitors, diodes. It has layers, which layers you're going to build the layout out of, and design rules, how you can, which sizes of transistors you can use, how you can put the layers next to each other, and so forth and so on. Various flavors of PDKs are available. So we have different processes that are made for general digital stuff, such as general purpose processes, high speed processes, low power processes, but they would all be digital. Then we have special processes that will be intended for RF designs and for example, for image sensors and such specialty type of applications. We have special processes for memory, such as flash and DRAM. They would be usually in a different fab altogether. And in all these processes, we may have various numbers of metal interconnect layers and how the metal interconnect layers are actually defined. So once we have the devices that are provided by the foundry, and we need to, again, pass some sort of interface up to the next level, and that interface, again, is this PDK with how you interact with the actual foundry and what you actually send to them to fabricate. The next level is the circuit level abstraction, and there we don't see the devices as a bunch of atoms or a bunch of materials that we process in a certain way, but we rather get a little picture of a transistor. As you can see here, this would be our transistor, and that is what a circuit designer sees. So using these transistors or these different devices that were provided by the foundry, we draw a schematic, and then we use a simulator such as SPICE to test and optimize the circuits. Okay. Usually the SPICE model or the device in the PDK allows various parameters that, and like the Cadence Virtuoso suite, they're called CDF parameters, that can be modified to optimize the schematic. These include, for example, what the length and width of the devices are, the number of fingers that the layout is going to be made with, different types of capacitances, resistances, the sizes of the diffusions, all kinds of things like that. We use a layout editor to actually go and draw the circuit, and then we can use a parasitic extractor to extract the RC values and run accurate post-layout simulations. So once we finish the circuit, we actually try to abstract that away. We try to measure different things such as the propagation delay and the rise and fall times, the power consumption of different toggling and so forth, and build some sort of gate, a digital gate that we can use as a black box and not care about how it's built underneath with transistors. And this is the gate level abstraction. So we abstract these things into black boxes that we're going to use as gates, and the gates are designed to with with the following characteristics: Boolean functionality, the interface, what types of pins or ports we have for inputs and outputs, what the delay and power consumption of these gates are, the capacitances that the input and output see, the size, the geometry of the gates, etc. Once a gate is abstracted, it can be used by higher level tools such as hardware description language tools. That leads us to the module level abstraction. So after we have these gates and we know how they act, and we don't and we can use them to build larger modules. So gates and other low-level circuits are connected together into modules such as adders, memories, etc. And these are tested for functionality and are abstracted for system integration. Usually the analog design skips this gate level, so it goes directly from circuit level. We provide this black box of some sort of analog. If it's an ADC or a PLL, it may use gates inside too, but often it has transistor level things inside it, so it skips the gate level abstraction. Digital modules usually go through the gate level, and we define full systems based on the digital models with hardware description languages such as Verilog or VHDL. We instantiate the gates, and we can instantiate these more complex analog type of modules. We use EDA tools, electronic design automation, to verify the functionality at all depth of the hierarchy. Finally, we get to the system level abstraction. And usually we draw an architecture of the whole system. This is a type of a block diagram that defines the interfaces, it defines the registers, the instructions that we can use, the control blocks, the buses, etc. about this. Okay, systems are usually implemented again with some sort of hardware description language. There can be higher level description languages such as System C that can be used for this. We usually verify the functionality with logical verification. We can also have different simulation frameworks above that. Okay, systems are defined to comply with standards and to implement protocols. We also have higher level abstraction, so we need to write programs. So programmers, they use high level programming languages such as C, Java, Perl, Python, etc. And so what we need to do is take these high level languages and compile them into assembly languages, and this is using a compiler. A compiler tries to optimize the instructions according to the actual architecture or microarchitecture that they're compiling to. And then the assembler takes the assembly and turns it into a machine language which we can load onto our actual processors. So that was our design abstraction, just as a very quick overview of where we are. And in this course, we're dealing mainly with the gate level abstraction and a little bit the module level abstraction, but we're discussing a lot of the device level abstraction because it affects us a lot, and a little bit looking up higher level. So the next step is the design metrics, and we're just going to do a quick reminder of the design metrics that we're dealing with. And before we start with design metrics, we have to remember the 4 words that every engineer has to know, that there's no free lunch except for this guy over here who's buying his free lunch for 10 bucks. So we have to remember that the job of a VLSI designer is to understand, design, and optimize the trade-offs between these 4 main metrics: performance, cost, reliability, and power. Okay, so in this section we'll go over the main design metrics for evaluating these design aspects. You can rarely improve all of these factors simultaneously. If you get a win-win situation and you can improve everything, then you're going to be a winner. Usually when we improve one thing, something else gets worse. So if we provide higher performance, it's going to cost us with more power, maybe more cost, etc. So our goal is to actually improve all of them. So let's start with performance metrics, and just as a quick overview, again, things that I expect that you already have heard. When measuring performance, we usually use these 2 types of metrics. One is the propagation delay of the circuit, and propagation delay is a differential type of a definition. So we have here the input voltage and the output voltage to some gate. Let's say we have an inverter or something like that, where here is V in and here is V out. And we see that there is some sort of rising input, and of course once we have the input rise over here, we're going to have the output fall on this inverting gate. So here's the fall at the output. Okay, the propagation delay is defined as how long it takes for the input to rise until the output falls for an inverting logic path. And usually we have to define some sort of a singular point where that happens. So for example, in this definition here, when the threshold of 50% 50% of the voltage, the supply voltage is crossed at the input until 50% of the threshold is crossed at the output. It can be using different definitions, such as 40% of the input to 60% of the output, or 60% to 40%. The most important thing is that our libraries are made to use the same metric. Okay. Anyway, so what we have here is once the input signal rose above 50%, we start counting until we get to the point where the output fell 50%, and that would be called our rise to fall transition. So we usually call it TPHL, or high to low. Okay. Similarly, if we are having the input fall, then until the output rises on an inverting gate, and so here the output is falling once it hits the 50% VDD until the output rises 50%, and that we get our TPHL, or our high to low transition. So again, TPD, or propagation delay, is between the input voltage and the output voltage. It's a differential type of a definition. Next to that, we have the rise or fall time definition, and that is not a differential type of a definition. It's defined on a single net. So each of these nets has or each of these signals has a rise and a fall time. And so the rise time of this is how long it takes for it to go from a 0 to a 1, and the fall time of this is how long it takes to go from a 1 to a 0. And again, here we have to define the singular points of where it passes. So often we use like a 10 to 90% definition, or we may, in this case, for example, as shown here, we use a 20 to 80%, and it doesn't matter as long as everything is apples to apples compared, and we're using the same definition for all of our gates. So those are our main performance metrics, but another thing that we can use and is often used as a kind of a normalization of propagation delay is what's called the fan out of 4. So we learned about optimal load driving and logical effort, and we know that we often want to have each gate drive a load that is 4 times its size, or 3.6 or something like that. But anyway, it brought in this common terminology of fan out of 4. So we want to see what the TPD of a single gate is when it's driving something that's 4 times as large as it, and that kind of normalizes the gate to see how good it is at driving a common type of a load. So this is a fan out of 4. We take one gate, we load it with 4 similar gates, and we measure the propagation delay of the gate. But how would we measure fan out 4 in a simulation? I mean, the common way would just to be, okay, let's take a pulse generator here, put a pulse in, and measure the TPD of this thing. Is that the right way to do it? Well, I'll ask you that. What happens if we take this gate again, and this is our device under test, and we drive it? Okay, we can connect a fan out of 4 at the output, right? And then we can again put on some sort of a pulse generator over here, stick in a pulse, and measure what the TPD is. So there's an inherent problem here. The inherent problem here is that this is an ideal source, and with an ideal source, what happens is that we take out different types of effects. Like what do we set as the rise time of this source? And that's a good question, because it really depends on the technology and the size of the device that it's driving. So what we will usually do, and this is a general methodology that is worth doing in all simulation, we will not drive a gate with an ideal source. We should drive a gate with another gate. So if we take an inverter here that is driven with a pretty ideal source, so this can have a really sharp rise time, then what happens is that if this has a fan out of 4, so if say this is a times 1 size and this is a times 4 size, we will get at the output, because of the load that it sees, we will get some sort of a fall that is shaped to what the technology usually, this has a T fall that's kind of representative of the technology and not ideal. And that will be a good kind of T fall to put as the input to our device under test. Doing that, we had to have this be times 4, so we better put times 16 over here to test our fan out of 4. And what we should usually do is just use the multiplier, the M. So that gives us the M parameter in our spice, instead of putting actually 16 inverters, or we can just use bus notation to put 16 inverters or buffers here as the load. Okay, so again, so we have here our first type of a gate here will be in order to shape the input transition, and our second gate will be the device under test that we're going to actually measure the TPT on. Okay, our third gate, of course, is the load, but is that enough? And this is a good question. Well, what's going to happen here is, so we're going to have our falling transition over here, and then this will rise with also something that is representative of the technology in the fan-out for load. But here we have very little load because it's an unloaded gate. And what's going to happen there is we're going to have a pretty sharp fall. And due to Miller capacitance that we have that connects the input and output through the gate to drain type of capacitors inside the inverter, what's going to happen is our capacitance is going to see a sharp fall over here, and it's going to make this capacitor look much bigger than it is. So that's not something we want to do. So what we should do actually is put some sort of a load on the buffer here to shape the output transition of this guy. So again, we're going to put something that will be, like I say, times 64 or so as the load here, and that will shape the output as well. And then our Miller capacitance will be dampened and won't be so substantial in the whole simulation. So this is to eliminate Miller capacitance. It doesn't actually eliminate the Miller capacitance. It makes it actually have a real effect and not a non-real effect. So to do such a measurement, we would actually want to use this setup of about 4 gates instead of just a simple, 1 gate type of a simulation. Okay, so we finished talking about our performance metrics for now, and let's discuss power metrics. So when discussing power, usually when we say power, we mean the average power consumption of a component. Average power consumption is 1 over t, t being the period. When we take an integral of 0 to t, the instantaneous power dt. Okay, since we're usually using a standard supply voltage, a DC supply voltage of VDD or something like that, so we can take the V times the instantaneous current I, take the V out of the integral, and so we have the VDD over the period integral 0 to the period time with the instantaneous current dt. That's the average power consumption. Okay. Other times we may discuss peak power, but this is less common. And peak power would be the maximum current we have times this VDD or this supply voltage. That will be the max of all the instantaneous power. So the power consumption is usually decomposed into 3 factors. Dynamic power is essentially the energy consumed during a switching operation. This is probably our main power component, or usually is, but it's also the useful power component, because this is what's actually charging and discharging our capacitances that represent our voltage levels and make our signals move along our digital system. Static power, on the other hand, is caused by leakage currents in steady states. If it's non-CMOS, it might be just these static currents that we have running from VDD to ground in steady states, and that's not good because it's not representing anything. It's just wasted power, in fact. And short circuit power, which is kind of somewhere in between dynamic and static power. It's part of the dynamic power because short circuit power happens during switching operations, but it's a direct current between the supply rails, similar to static power. So it's this dynamic power that is wasted due to allowing a resistive path between the rails, and it's just wasted power as well. Okay, so going a bit deeper into dynamic power, the energy required to charge a capacitive node to VDD is approximately the low to high energy is the switching capacitance times VDD squared. Okay, if we have a circuit that's operated at a frequency f, then the dynamic power is just f times the switching capacitance times VDD squared. F, of course, is 1 over t, the period, the clock period. But during each clock period, not all the circuit capacitance switches at every cycle. In fact, what we say is the percentage of the capacitance that's switching is some sort of a factor of the total capacitance. So the switching capacitance, we can call it some sort of alpha times C total, where alpha is the activity factor. So we get a final expression of P dynamic is alpha times F times C total times VDD squared. Often alpha can be as low as 10%. Both static and short circuit power are caused by current flowing between the supply rails, as we said before. Static power is due to leakage or static currents in the steady state of the circuit, so it's the static current times the supply voltage. Short circuit power is due to low resistive path between the supplies during a switching event. Both of these types of consumption are unwanted and should be minimized. So that's a short discussion of power. And we'll go to the next metric, which is reliability. So reliability is the ability of the circuit to provide correct results during all operations throughout the lifetime of a system. So far, the only thing that we've really discussed with reliability is the digital noise margin metric. So the high noise margin is the high output level minus the high input level, and the low noise margin is the low input level minus the low output level, and the noise margin is the minimum of the low and the high noise margin levels. That's the only thing we really discussed so far, but in this course we'll discuss further reliability aspects such as what SRAM reliability and noise margins are, a little bit maybe about what aging is. We kind of discussed things such as electromigration and hot electrons and so forth that affect reliability over time. And finally, our last category of design metrics is cost. So it's all about the Benjamins, as they say, and even here in engineering, usually what we do is the applicativity of science, and it all comes out to making some sort of a product that can be either sold or used, and so cost is a very important part of it. Okay, the only cost feature we have previously considered is the area size of a transistor or a gate, but we never actually quantified it in terms of prices. It's an important enough issue that it deserves a section on its own, and we'll discuss that after a short break for the Computer Hall of Fame. So after discussing some of these big computers, these big original computers, I wanted to go into actually what is a bit more closer to home, and that's the IBM PC, which is the computer that actually brought computers into our home. Okay, so IBM, or Big Blue, was a huge company that made these mainframes that were used all over the world. And there's a famous quote that IBM bringing out a personal computer would be like teaching an elephant to tap dance. But in 1981, they did introduce the IBM PC and sold it for a price that anyone could buy, I guess, with quite a big, quite a lot of money for $1,500. In any case, it was a big risk that IBM took, where they went from this enterprise type of big multi-100,000 or more of that price computers down to this thing that people would buy, a commodity type of product that would go into people's home. But amazingly, it came out to be the most successful computer of all time. And not only it ran on an Intel 8088 processor that was developed here in Haifa by a guy I know, Rafi Retter, and it was one of the biggest successes that made Intel what it is today. Okay, it ran at 4.77 megahertz, a whopping 4.77 megahertz. It had a huge 16 to 256 kilobyte memory. Okay, I was saying that sarcastically. Obviously, these are numbers that are very strange to us, but then it was pretty substantial. It was cheap for then, so you could sell it to somebody at home, but still, these were numbers that you would find in these types of home computers. Along with its release, a new operating system called MS-DOS introduced Microsoft to the world. So this kind of holy trinity, IBM, Microsoft, and Intel, which have led our worlds for many years since then. Actually, IBM, again, was a big, huge monster already in those days, but Microsoft and Intel really were kind of born through this IBM PC. So it not only brought computers to our home, but it also brought Microsoft and brought Intel to our lives. Okay, that leads me to the third part of our discussion today, which is a model about the cost of an integrated circuit. Okay, so how much does it cost? In the end, it all comes down to cost. Okay, cost can come in many ways, but to get a basic understanding of this concept, let us develop a simple cost model for an integrated circuit chip. Okay, so before I start, I want to discuss two important types of costs, which are true to all engineering projects, but specifically for chip design, we discuss them often. So NRE, or non-recurrent engineering costs, are one-time cost factors. They include the design time and effort, so actually the salaries that we pay to our engineers and so forth. But in VLSI, they have a huge additional factor, which is the mask generation cost. So when we send the tape out to the fab, we actually make the masks, and you can see here over the years that the prices of mask generation went up really high, and we're talking about several $1,000,000 for a tape out, several $1,000,000 for mask generation. So that's a big component of the non-recurrent engineering costs. The second category is recurrent costs. So if NRE is a one-time cost factor, recurrent costs are what happens that we need to actually put out for every single chip that we sell. So this includes the silicon processing, the packaging, the testing of each chip, and it's proportional to volume and proportional to chip area. So the more we make, probably the cheaper it's going to be to do this, just because of prices, but it for sure is proportional to chip area. The bigger the chip, the more it's going to cost for recurrent costs. And we'll perceive all these things through the model, the simple model that we're going to develop now. Okay, so our simple model is just going to take us through a rough overview of what a chip costs. It's actually much more complex than this, but this will give us a good understanding of how it works. So the general cost per IC, and again, this could be any product in the world probably, but specifically for integrated circuits, it's pretty much true. So the cost is the variable cost, these recurrent costs, plus the fixed cost, this NRE. So this is the recurrent cost, and this is the NRE. Okay, and we have to divide the NRE by the volume. So, in other words, if we're going to make if we're going to pay engineers and we pay them some amount of money to design the chip, and we sell 1,000,000 chips, we can divide all of the payments we made for the whole time with them by the number of chips we made. Or this tape out price, if it cost us $2 million to tape out the chip, and we sold 2 million chips in the end, we could actually say that the mask cost was only $2 per chip. That's not true for the variable cost. So if each additional chip costs us another $1, it's going to cost us another $1 regardless of if we made 1,000,000 of them or 10 million of them. Of course, there is a difference between if we make a small amount or a big amount. The larger the amount, usually the price per chip will go down, but it's less substantial than the fixed cost, which actually is directly divided by the number of chips we actually sell. So the fixed cost, again, is many different factors. It includes the air conditioning of the building, or the lease that we have on the building that we're renting, and so forth. Maybe even the company party that we threw. That all goes into the NRE. But the variable cost per IC is kind of an important thing that we can break down into another model. So let's see what the variable cost is. So we can say that the variable cost is the cost of each and every die, each and every piece of silicon that we made. But we take that silicon and we package it, and the package and the assembly, they cost money too, how we actually put the die inside the package, and we have to test that. And that also costs money. The tester is an expensive piece of equipment. It sits on the tester for a certain amount of time, has to run vectors through it, verify that it actually works, and that costs money too. So when we add those three together, we find out that some of those chips that we made actually weren't good. That's why we run the test, so we throw some away. So we have to divide this by the final test yield. What is yield? Okay, yield is basically the number of good chips divided by the total number of chips times 100%. So it's the percentage of chips that we tested that were actually good. So we want to get 100% yield, and then our variable cost would just be die cost plus package cost plus test cost. But since we throw away some of them, we divide it by the yield that we actually get. So I'm putting those expressions over here on the side, and we'll go into die cost and see what it's all about. So we can see here a wafer, and this is a wafer from AMD, and you can see that it's diced into some sort of rectangles. Okay, and what we have here, each one of these little rectangles is a single die. So the cost of each one of these dies, which is the die cost over here, it's the cost of the entire wafer, because the entire wafer has to be processed. Each wafer is processed as one unit. We process the wafer, so that costs a certain amount, and we have to divide that by the number of dies per wafer. But that's not enough. We also have the die yield. So with the die yield, we'll actually have a prober that will, a big piece of equipment that will come down and stick some probes into each and every chip here and run as many tests as it can on the chip, and it will mark them, and we'll put a little dot on the ones that are no good. and then another machine will come and it will throw away the ones that are no good. And that's very important because the ones we threw away, we don't go over and package and run another test. So that we call the die yield. So there's an initial yield that we get on the tester itself before we actually pay for the package, and another test that we run after we've packaged it and assembled it, and that's the final test yield. So these are two times when we're going to actually throw away dies, and so there are two types of yield over here. Let's look at the dies per wafer. How many dies do we actually get per wafer? So as you see, that the wafer is round due to the manufacturing process of the wafer, but our dies are rectangular because of how we actually dice them, how we cut them. And you see here on the left we have a wafer that has these big dies. There are only 4 dies in one wafer, and on the right here we have smaller dies. And what we can see is that the size of the wafer, the size of the die really sets the number of dies we get per wafer, obviously, but it also sets how many dies we lose at the edge, because you see it's round, so we have these edge losses, and we lose a much more substantial number of dies on these big. The larger the die is, we lose a lot more of them due to edges than we do when we have the smaller dies. And there's a nice expression here that tells you how many dies we get per wafer, and you can see that both of these are proportional to die area. So the larger the die is, the fewer dies we get per wafer. What is the wafer size? Well, there's a kind of a Moore's law of wafers, and we see that the wafer size has grown. It grew from these small 100 millimeter wafers until we got to the 12-inch wafers that we use today. Okay, on this graph here that it still appears on the internet for mini silicon, they expected that in 2017 we'd be using 450 millimeter or 15-inch wafers. That has not happened as of now. The reason it hasn't happened is not that it's not wanted. Everybody wants to have bigger wafers, then you get more dies per wafer, and then the cost of die would go down. The problem is that the machinery that actually processes the wafers is built exactly for one size of a wafer. The machinery is built for 12-inch wafers, and it actually knows how to make a die that's over here and a die that's over here and a die that's closer to the edge and a die that's closer to the middle exactly the same with all the processes. And that's a pretty complex thing to do. If we make the wafer bigger, we have to have a larger area that everything has to be exactly the same at. It's much harder to do technically. It also means we have to replace all the machines in the fab, which is a really high expense. This is something that has been so complex engineering wise that we're stuck with the same wafer size since about 2001. So we're talking about 20 years of using these 12-inch wafers at high-end fabs. Maybe one day we'll get to the 15-inch wafers, but so far it hasn't happened. Actually, if we would have gone by Moore's law already back in the early 2000s, we would already have huge wafers, and that, as you know, did not happen. I want to discuss defects for a second, which is this die yield over here. So what we usually get in a process is we get a certain number of defects per square inch or square centimeter. So it's kind of a statistical thing that we know how many defects you're going to have on a wafer. And we have a wafer here that has these 7 defects that are scattered around. And this is the same wafer as before that was diced into 4 chips. And what we see is because there were defects on this chip, on this chip, on this chip, well, we got some pretty bad yield. In fact, only 1 out of our 4 chips actually came out good. We had to throw away the other ones during our die testing, and we got yield of 25%, which is really poor. Well, if we would have used a smaller die size, like in the picture that we had before, and we have the same exact defects, you see the scattering of the defects, it didn't know about the size of the die that was underneath. Well, now we scattered around these defects, and if we count, we actually got 19 out of the 24 dies that we were supposed to make were good. So we got a 79% yield, which is much higher. And this leads us to an interesting conclusion. The die cost is a function of the die area, or it's proportional to the die area to the 4th. So the larger the die we get, the worse yield we get, the fewer chips we get, the more edge losses, so the fewer chips we get per wafer. The die cost, again, is really poorly proportional to the die area. And that's the bottom line of why area is so expensive. The larger the die, the more it costs. And so a smaller die is really worthwhile. Okay, so let's summarize this whole model that we said here. So the basic cost per IC, the total cost, is the variable cost or the recurrent cost plus the fixed cost or the NRE divided by the volume. When we take this variable cost, it's basically the die cost plus the testing cost plus the packaging cost, and we have to divide all that by the number of dies that actually come out good after we package them. So we divide it by the final test yield, where the yield is the percentage of the good chips. Okay, this die cost is the cost of the wafer divided by the dies per wafer times the die yield. And the dies per wafer is actually dependent on the edge losses, and it's according to this expression down here. Remember the two types of yield that we're discussing here. This one up here is after packaging, so we already paid for the package and the final testing on the tester, versus this one, which is before packaging. This is just testing for defects, whatever we can do at the level of the wafer with the probe station. And just remember that die cost is proportional to die area to the fourth. That means that the larger the die, really the more expensive it gets. So I found a nice example here from this report here from a long time ago, from 1993. And you see here different chips that were popular. So we have the 386DX and the 486DX2 from Intel. We have the IBM PowerPC, HPPA, the DEC Alpha, the Super Spark, and the Intel Pentium. And these were chips that came out up till 1994, and you see different statistics about them. So you see there were only a few metal layers on these chips, not like today where we have 10, maybe even 20 metal layers. Then it was just a few. Okay, you can see here the line width, we're talking about 900 nanometers, whereas nowadays we're talking about 7 or 5 or even 3, even 2 nanometers is what they're starting to talk about nowadays. So these are pretty old processes. The wafer cost, well, you see that the wafer costs aren't that big. There's not that huge a difference between them. Okay, the wafer cost is kind of dependent on the manufacturing process, and it's pretty much the same across the different chips. And therefore, also in the different manufacturing fabs, the defects per centimeter square is also kind of the same between the chips. So the wafer cost and the defects is kind of a given. The die area really depends on the product. So the 386 had a small 43 millimeter die. The 486 had about double the size 81 millimeter die. And then you had some of these much larger dies. So the DEC Alpha had really a 234 millimeter die, and the Pentium was already almost 300 millimeters. So they're much larger. And again, what we expect to see is that the die area drives the cost up to the fourth, right? And dies per wafer, so we get a lot of dies per wafer for the small die, whereas we get a real few dies per wafer for the really large die. So that's one of the things that drives the cost up. But the other thing is the yield. So the yield for the smaller chips was 71%, 54%. I imagine it got higher as the process got more mature. But if you look at the Pentium, we already had a 9% yield. That was really low, and it was probably due to the large die size. You can see similar things here with the DEC and the Super Spark, where we had really low yields, and that really drove the price up. Now, if you look at that means that the die cost itself, it was only $4 for the 386, $12 for the 486. But when you go over to the higher end things, we had $149 for the DEC Alpha, $272, and because of the really small yield and the few dies per wafer, each die of the Pentium, the original Pentium, cost $417, which is a whopping payment for the basic price of each die. What about packaging and test costs? So we see the die costs over here that we got to on the previous slide, right? And this is the number of pins. So the 386 and 486 only had a bit more than 100 pins, but on the bigger chips like the DEC Alpha, the HP, we had a lot of pins, and they already needed PGA packages, much more complex packages than these QFP packages that we had below. And that's why these packages for the 386 and for the PowerPC, they were extra cheap, right? But then again, the packages for these PGA packages for these guys was much higher than that. I mean, we're talking about 35 times the cost of the 386 package, right? Test and assembly also didn't cost that much, only $4 for the 386, whereas these guys, they cost already, closer to $20-30 to package them. Okay, so the total price of the chip was the die cost plus the testing and the packaging. Well, for the cheap 386DX, you can see that the test and the assembly and the package costs were even more pricey than the chip itself. The total cost was $9, and again, over 50% of that was test, assembly, and package costs. Then again, when you go up to the more high-end things, so for the Pentium, you had a total cost of $473. The test, assembly, and package costs are only a small percentage of that. But how much did they actually sell these things for? Okay, that is also interesting. So the 386, they sold it for $31, which is a nice multiple on the price, but the actual absolute sale price is only $22 over the cost of the die. And the reason that it wasn't that high is because they had intense competition, and at that time the AMD processors were big competitors to the 386. What happened was, around that time, AMD kind of fell out of the race, and the Intel became the only player, and they were able to sell their 486 DX2 for a whopping $245. So they already got a much higher margin on the price of the chip. Okay, you can also see the DEC Alpha. The DEC Alpha had a lot of innovation. There was a lot of R&D. So they took a $202 chip and they sold it for $1,200, and that was probably to recoup the very high NRE expenses they had to develop this chip. With the Pentium, they also had a real high price tag on it, and it's actually an absolute number. It's really big. That was about $500 more than the chip cost, and that's because they were able to get out early shipments. It was a big innovator in its field, and so they were able to sell it for a high price. If you look at Aptiva in 2014, kind of just to give us some basic numbers, the cost of chip development, the NRE, and there's a large spectrum here. So if we take the hardware development, the engineers, anywhere from like $300K to $200 million for developing a chip. Software development, again, you don't have to do any software, and then it would cost nothing. But if you really want to sell something, it can cost up to $800 million. So it can cost much more than even the hardware development. IP licensing, that means how much are we paying other companies, these IP vendors, to use their chips. And there are two ways to do IP licensing. Either you could pay up front, and that's what this is talking about. So either we don't pay anything up front, or we could even pay up to $10 million just for IP. But we can also pay royalties, which we'll see on the next slide. EDA tools, so we have to pay, our guys Cadence, Synopsys, Mentor, etc. for their tools. So we could also make them in-house, and then I guess it would be free, or use open source tools, but usually we're going to pay several million for these EDA tools. The chip tape out, again, maybe it's a really old process or something like that, and it could be a low price. It might be on a shuttle, and we could pay $100K, but tape outs can cost $3 million, and I can tell you it's even more than that for the newest processes nowadays. Test development, again, test development can be real small, just a few $1,000s, or it may be up to the millions. So if we take the total NRE, we're going on a range from $1 million for a chip, and I don't know any chips that have been made for $1 million, but it can be even $1 billion just to develop a chip for NRE. Okay, what about the cost per chip, the recurrent cost? So the die cost, it can be as cheap as 10 cents a chip, but it can go up to like $1,000 a chip. As we saw, the Pentiums were really expensive. And it can be even more than $1,000 a chip, I'll tell you that. Packaging, again, packages can be really cheap packages. They can be a few cents for a package, but they can go up to really expensive packages where even at volume, they're going to cost me several dozen dollars for a package. Okay, assembly, that means connecting the chip to the package. Again, it can be real cheap, or it can be a more complex process. It can cost several dozen dollars. Testing, we don't have to test very much, or we could somehow eat it up in our other costs, or it can cost quite a substantial amount to test a chip. IP royalties, so if it depends on the deal we have with the IP vendor, we may be paying a few dollars out of our total chip cost for IP. And so the total recurrent cost can be as little as 30 cents, but as high as even $1,000 or more dollars for each chip that's made. So that was our basic model for how much a chip costs, and that's based on the references over here. And that's the end of this lecture about design metrics.